Good morning. Are there any questions before we get started? Yes? I know I believe the median was 84. All right, I can get the statistics. You should probably all have received Wayne and Harry and I worked till 5 on Friday grading all of your exams, and then I got them all posted. So I assume you've all seen your midterm grades, midterm scores. So the class overall did really quite well. I mean, the whole class did very well. I can get the statistics for you. Maybe I'll get a box and whisker plot for you. All right. This week I want to get started on putting you into groups for the project, and for you to see what the projects are and to get signed up for projects. So essentially we will be, I'll be creating a survey questionnaire kind of thing, and based on that and knowledge of your GSIs about how you work in R and that sort of thing, we'll be making teams of 5. So you will be assigned to a team of 5. You can request to be part of a team if you have very strong preferences. And then we'll post a list of projects, and your team will choose a project. And so probably half of the section times going forward will be spent working on your projects. Yes? Well, so one of the things that I'm going to try to do is first find out your section and then what other sections you can possibly also attend. And so groups might cross sections if you have flexibility in which section you could go to. Right. Yes. Any other questions? So today we're going to wrap up our discussion of probability with one last result. And also, if we have time, I'm hoping we can wrap up hypothesis testing as well. So we're going to start with the central limit theorem. And the central limit theorem, it goes sort of hand in hand with the law of large numbers. We saw the law of large numbers more than a week ago in class, probably a week ago Friday. The law of large numbers says that as you draw more and more tickets from the box, the sum of the draws approaches the expected sum, which is n times the box average. But where the deviations that you might see get larger and larger as n grows, and that's like the square root of n times the box SD. Where on the other hand, the average of the draws that you make from that box, that approaches the box average, and they get closer and closer to the box average. The spread of what you might expect to see decreases like the SD of the box divided by the square root of n. So in one case, things are still centered around the box average, but the spread is growing like the square root of n. That's how the sum works. And on the other hand, the average is approaching the box average, and the spread is decreasing like the square root of n, divided by the square root of n. So the central limit theorem is also related to what happens as n grows, not just to what you expect, but to the whole probability distribution of what you could draw. So remember, there's a probability distribution hanging around under there of saying, oh, I could get all of these different possible results, and what's the probability I get those? You know in a 0-1 box that if you're drawing with replacement, those probabilities are being defined by the binomial distribution. And so in general, we want to say, okay, what happens to this probability distribution as I draw more and more tickets from the box? So we have a box. We don't know necessarily what's inside the box. We have a box average and a box SD, and we're drawing n times with replacement, and n's the thing that we're going to change. So what does the probability distribution for the sample average look like? We're going to, before we go to the sample average, Let's go and look at something we know really well, and that's the 0-1 box and the count from the 0-1 box. So let's review the 0-1 box, where we have P tickets marked 1 in our box. So we know the box, P is a proportion of tickets marked 1. We know that the box average, therefore, is going to be P, which is a proportion of 1s. And we know the box SD is the square root of P times 1 minus P. And as I mentioned just moments ago, the law of large numbers says that the proportion of tickets gets closer and closer to P the more I draw. And the count of the tickets gets heads towards n times P. The expected is n times P, but the standard error is root n times P times 1 minus P. So what happens to this probability distribution? We know it's a binomial. So I guess what I'm saying is, what does the binomial look like as we draw more and more tickets from the box? So I've put 4 examples up here for us to sort of look at and maybe make some guesses as to what happens. The top left is a binomial with n is 10 and p is 0.2. And you see that we know that with a count we expect 2, and we expect the numbers to be pretty small because the chance of getting a 1 is small. And so the chance of getting a 6, 7, 8, 9, or 10 is quite tiny for drawing 10 tickets from the box. But what happens when we keep drawing tickets from that same box with proportion of 0.2 of the 1s in the box? That's on the right-hand side, top right. There you see that although the range of possible counts coming from that box runs from 0 up to 100, by the time you get to 35, the rest of that stuff, 36 and above, is practically negligible. And so I've zoomed in on just the region from a count of 5, so drawing 5 1s, to a count of 35. Now we know again that the expected count is 100 times 0.2, which is 20. And we know the spread of the count is the square root of 100 times the square root of 0.2 times 0.8. And we can do that mental math, hopefully. Square root of 100 is 10. The square root of 0.16 is 0.4. And so it's 4 is the standard error. And so notice how there we are with a distribution centered at 20, nice and symmetric looking. And the spread is about 4. And does that look like another distribution that you've seen so far? Yes? It looks like the normal to me. Yes, it does look like the normal. And so even though we've got a box that's got, for example, 2 1s and 8 0s in it, and when you first start drawing, you have a very skewed probability distribution with a very long right tail. As you draw more and more tickets from that box, the probability distribution starts to look relatively normal. So let's look at other values for P. If we have P as, look at the bottom left here, P is 0.5, and we're drawing 10 times with replacement. We know that we expect 5, and that's right here in the center, smack in the center. We already have something that's symmetric and nearly normal looking with just 10 draws from the box. So what about having a box that's full of 1s? For example, 90% of the tickets are 1s. So we have a binomial with 0.9 as our probability. Here I've picked a huge N, 250. And so the expected value is 225. That's the expected count. And you see, again, we've got something that's nice and symmetric and looks quite normal. Now, the only difference between, or a difference between the binomial distribution and the normal is the normal is a smooth distribution. And underneath that, sort of like our density plots, area equals percent. Whereas here, I've got these spikes, And that's because I know I can only possibly get 225 or 226 or 227. So what I'm going to do in the next picture is I'm going to take that probability, I'm going to smooth it out across a bar, so to sort of make a histogram from the binomial. And so on the left is my probability mass function, where each little line segment, its height is the probability, whereas on the right, I've now smoothed things into little bars where the probability of a 20, for example, is the width of the bar, which is 1. I've gone from 19.5 to 20.5 times the height of the bar. So I've now converted that into an area kind of calculation. And I've overlaid the normal, the normal curve, the normal density on top of it. Because with a normal, it's smooth, and we think about trying to approximate or find probabilities using the normal by the area underneath the normal. So if I were to say, well, what's the chance I got a 20 ones, a count of 20, when I draw 100 times from this box, I could find the exact chance by getting the area of that bar. Or I could find an approximate chance by looking at the probability of a normal falling between 19.5 and 20.5. Now, some of you might be saying, well, we haven't really seen the normal before. We've kind of talked about it. But what do you mean by normal 24? So by that I mean that it's centered at 20 and has a spread of 4. And so far we've basically been looking at the normal 0, 1, which is also known as the standard normal. But in general, there's a whole family of normal distributions. And you describe the normal by its center and its spread. Here are 4 of them that I've put all on the same plot. These are all from the normal distribution. They just have different centers and different spreads. Notice that their shapes are all roughly the same. So the black one that I started with is the normal 0, 1, which we call the standard normal. It's centered at 0 and has a spread of 1. Remember the rules that we talked about for the area under the normal? Between plus and minus 1, the area is 68%. Between plus and minus 2, the area is 95%. Between plus and minus 3, it's 99.8 or 9%. So that's the normal shape here. Now, on the other hand, if I just increase the spread, but keep it in the same location, so I have a normal 0, 2, well, to increase the spread, that normal curve has to come down more to have its area spread out more. And that's the orange curve, is a normal 0, 2. So that's what happens when I change the standard deviation or the spread, but I keep it centered at the same place. On the other hand, I could shift and say, oh, I want to look at a normal which still has a spread of 1, but it's centered at 4. That's the green one. So that's the exact same shape as the normal 0, 1, but it's just shifted so that it's now centered at 4. So the green one is a normal 4, 1, centered at 4, spread of 1. And then on the other hand, I could have a spread that's smaller than 1, and that says that you're going to find more mass or more area close to the average, and that's a normal 4, 0.75, so it's more peaked. But all of these have the same general shape. Yes? How do you exactly calculate? So there's an actual functional form for the normal. This is a curve based on basically the exponential function. So it's the e to the, and then it's minus 1/2, and then the quantity is x minus, so x is the x according to the x-axis, x minus the center, divided by the spread, quantity squared. So that's the functional form for each one of these, but they have a different center and a different spread. So I've now forgotten your question. What was your question? A graph meaning you've given data? Well, so it's inherent in the normal curve now. So basically what I've said is, here I'll write it like this. you have e, there's a quantity out here to make it integrate to 1, but e to the minus 1/2 x minus the center divided by the spread squared. And so if you know the center and the spread, that tells you what the function is. So if you're observing data that you think follows a normal, you take the average and you use that for the center, and you take its SD and you use that for the spread. Is that, that's what you were looking for? Right. Now, on the other hand, with the binomials that we were just looking at, these guys back here, I know the binomials expected value or expected center and its spread, its SD. And so what I'm doing is I'm taking that and I'm plugging it in for the normal to see how close they are, so how close they match up. So I know the expected for the binomial is 100 times 0.2, which is 20. And I know the spread for the binomial would be the square root of 100 times 0.2 times 0.8, which is 4. So I'm plugging in for the normal, for its center and spread, what the binomial's center and spread are, and overlaying the two. Okay? Are there other questions? That's a good question, because I'm now about to sort of look at a different box altogether, a different probability distribution altogether, and then I'm going to ask you to step in and come up with some examples. So that's the normal. And we could even go so far as use R to compare the probabilities under the probabilities that we know for a binomial to what we would approximate for a normal. So I've given you the R code here of, suppose you wanted to know for this same binomial, what's the chance of exactly 20 successes in 100 tosses? So we could use the dbinom function and say, hey, give me that probability of 20 successes in a binomial with 100 trials and 0.2 of success on each trial. And it comes back with a 0.099 to 3 decimal places. Then we could say, okay, let's use the normal curve to approximate that. So here again, we're looking now at areas under that normal curve. And so the area is going to go from 19.5 to 20.5. So I used the p-norm function. And remember, p-norm says, give me the area to the left of 20.5. And then I subtract the area to the left of 19.5. And that will give me the area between 19.5 and 20.5. For the normal with a center of 20 and a spread of 4. And so we see here that 0.0994. So it agrees to 3 decimal places. So this approximation is really quite good. I could also ask for the left tail. Like, what's the chance of 10 or fewer successes? Well, the p-binom function tells me that 0.00569 or whatever. Now, the normal approximation, we'd look to the left of 10.5, remember, because we're looking at the area and we've got those bars of width 1. So the p-norm of 10.524 is 0.08. So it agrees to 2 decimal places, and it's off a little on the 3rd decimal place. But still, that's a pretty good approximation of the binomial with the normal. Any questions on that? So what about other kinds of boxes aside from 0-1 boxes? So we now are pretty sure if we have a binomial distribution that as n grows, that binomial probabilities start to look like normal curves. But what if we're drawing from some other box that isn't just a 0-1 box? What does that look like? So here's a really simple one. We have a box that only has 3 tickets in it, a 0, a 2, and a 4. So I can really easily compute the average, that's 2. I can also compute the SD, which is 1.63. And remember, the expected sum of the draws is n times the box average, which is 2n. And the standard error for the sum of the draws is 1.63 times the square root of n. So then the question is, what's the probability distribution of the sum? Well, that kind of depends on what n is. So rather than compute, now it's hard. I don't have it would be very hard for me to actually say, well, with 100 draws from that box, here are all the possible values and here are the exact probabilities, which I can do with a binomial. But I can use R to take 100 draws from that box, look at what I got for my sum, take 100 draws from the box, look at what I got for that sum, take another 100 draws from the box, look at what I got for that sum, and replicate this 100,000 times, every time computing the sum of 100 draws. So now I'm getting sort of an empirical version of this unknown probability distribution. So, so I can take here's this, replicate 100,000 times the sum of the sample from the box of 100 draws where I replace equals true. So you guys have used these, you've used this kind of notion of finding approximate probabilities before. I'm just doing the same thing again. So I'm going to get 100,000 different sums. And now I'm going to look at all the different possible values they could take on. And so on the left-hand side, I've made a density plot of the average 100,000 averages of 100 draws and overlaid it with a normal curve where the normal exactly matches the mean, the center, and the spread of what I expect from my box. So remember, if I back up, the center is 2, and I'm drawing 100 times. So again, it's 2 times 100. So it's 200 is what I'd expect. And the spread is the square root of 100 times the SD of the box, which is 10 times 1.6, so it's about 16. So center 200, spread 16. So center 200, spread 16, that's the, so I drew, or I plotted a normal curve with a center of 200 and spread of 16 on top of my empirical, what I got when I replicated 100,000 times. And you can see it's not exact, but it's pretty darn close. The only place where it's really off a little bit is there's a little bump up there near the center, near the 200. So lots of times it's really hard to see how well things match, and so instead what we do is we match the quantiles. So we, way back, probably 5 or more weeks ago, we looked at quantile plots when we wanted to compare two distributions. So what I've plotted on the right-hand side are the quantiles of my 100,000 sample averages against the quantiles of the normal distribution. And if they have remember, if they have the same distribution, I should get roughly a straight line. Now I've got all these tiny, if you look, the black are, they're kind of little steps, and that's because when I draw 100 draws from that box, there's only, I can get something like 150 or 151 or 152, but I'm not going to get 150.25 for my sum. And so that's why they're those little steps. And I've drawn a line, a straight line through it. If I get a straight line, then that says I've got something really close to a normal distribution. And so here I've got a box that's got a 0 in it, a 2 in it, and a 4 in it. I draw 100 times with replacement, and I look at the sum of the draws, and I say, well, what's the chance I would get a 200? Or what's the chance I'd get 225 or above? Or what's the chance I'd get 175 or below? And those chances are very similar to what I would compute using this normal with the same center and the same spread. So that's called the central limit theorem. All right, so now I'm going to get you guys to see if you can come up with a box where the normal curve doesn't turn up. You can have 10 tickets, and that's it. So what I want you to do is play around and just come up with what you think would really make it hard to get a normal curve out of it. So in other words, when I draw a certain number of tickets from that box and look at the sum and look at the probability distribution of the possible values for that sum, it doesn't look normal. So you get 3 minutes. You can talk with your neighbors, and then I'll record what you want to do. So if you've got 10 tickets, that means I need the different ticket values, and how many of each type. Okay? So come up with a, I'm going to switch over to this document camera. And what I want you to do is come up with a little sort of distribution table for your box. So whatever you want to put in here. So here's what I did was a 0, a 2, and a 4. And I could have 3 zeros, 3 2s, 3 4s, and then a 5. And that's for a total of 10 tickets. And that's my box. Do you think this is going to be a really... do you think this box of tickets is going to actually wind up having the sum follow the normal distribution or not? Well, I've started off with a distribution that did really well. In other words, it turned into something very close to the normal distribution. I've only added one ticket, right? So probably not. So you probably don't want to do something like what I've shown you already. So why don't you take 2 or 3 minutes and just come up with some ideas, and I'll record them over here on the document camera, and then we'll go into R and actually try to see if we can get a normal distribution by drawing enough times from your box. All right. Yeah. Well, I don't want you to know what it says yet. But what I would like you to do is try to come up with we're gonna get there. But what I'd like you to do is come up with just some kind of box where you think when you draw enough times, it still won't look normal, even though the examples I've shown you so far, they all look normal. Boy, you guys are quiet. So that means either you're still waking up, or you don't know what to do, or both. So, yes? You think you've got one? Oh, good. I'd like to write yours down and a few others. So what do you think?
What if we just had a box with all the same numbers?
Oh, that's a good one. Okay, but all right. So any number?
3.
The number 3. And why 3? Just 'cause? It's your favorite number? Do you know the story that number 17 is the only truly random number? Have any of you heard of that story? No? Well, because when you talk to people and you say, just pick a number, any number, just any random number, nobody wants to pick a number bigger than 20. And all the even numbers don't really seem like they're random. You got to pick an odd number. And anything less than 10 is kind of lame, and 13's unlucky, and 11's too close to 12. And pretty soon, you're down, and 15's like, that's not a prime, and so you're down to 17. And that's the the only really random number?
People
Anyway.
actually choose 17.
So that's what people claim. That's what 17 appears more often when you just ask people to come up with random numbers. Whether or not that's actually true, I don't know if anyone's done a study. So this is your value, and this is your counts. Did anybody come up with anything different? Yes?
How about 5 zeros and 5 tens?
5 zeros and 5 tens. Somebody else? Yeah?
What about 9 zeros and 1 10,000?
And 1 10,000. So 0 and 10,000. 9 and 1. Anybody else? Yeah?
1 1.
And? You have to have 10 tickets. Oh. Yeah. So you're essentially trying to say the same thing as the first group, only put one number in the box, right? Right. Anyone else? Warren?
Well, I was just going to say that those two boxes on the bottom, there's
Uh-huh.
no difference between them and the 0 1 box.
Which two?
The two that you've written for this count, the one with the
I like that observation. Very nice observation. So Warren's saying, well, there's no real difference in those two boxes on the bottom between 0 1 box and those. Do you agree with him? I do. I think he's right. There are only two values. And so you could take that 0 1, a 0 1 box, and you just rescale it, right? You just multiply everything in the box by 10, and you get, if you had a 1 0 or 5 zeros and 5 ones, and you just multiplied all the numbers in the box by 10, you get the one on the bottom left. And if you had 9 zeros and 1 1, and then multiply them all by 10,000, you get the one on the right. And therefore, what can you tell me about that? Well, they are not normal, but if I draw a large number of draws from the box and look at the sum, the probability distribution will look normal. So in other words, this one on the bottom left, we've already looked at with a 0.5, a binomial 10.5 was already, it starts out really symmetric. The other one we've actually looked at in a way as well, right? That was the 0.9 binomial that I looked at. This is a 0.1 binomial, which is just the flip of it. So good observation. So what about the one in the upper right? In fact, you've found a degenerate case. There is technically, what's the SD of that box? 0. And so you know every time you're going to draw from that box, you're going to get the same thing. There's also a degenerate normal. So I can go right back at you and say, yes, but it's a degenerate case. You get some, but that's kind of lame, but it's still true. Any other? So in other words, we need more than two values on our tickets. Otherwise, we're just reducing to the kind of the same binomial case. So does somebody else have? And one value is a degenerate case. So how about someone giving me another kind of box? Anybody? We can work on one of these as well just to confirm that that's indeed the case. But does anybody have a different box? No? Why don't I take this idea of a 0 and a 1 10,000 and just modify it a little bit? What if I have val of a bunch of zeros, some ones of 5, and I won't go all the way to 10,000. I'll just go to 25. And what you're trying to do is have a lot of one number and very few of another. So how about if I do 5 zeros, 3 ones, 1 5, and 1 25. That's a different kind of box. Right. All right, so let's take a look at these two. Let's actually take a look at these two and see what we get. Okay? So the one box has 9 zeros in it and 1 10,000. And the other box has 5 zeros, 3 ones, 1 5, and 1 25. So now let's go back to the laptop here. And I was practicing a little bit. So here are the values. Let's start with the one that just has a 0 and a 10,000 in it. And the counts for those are 9 zeros and 1 10,000. And then I'm going to make a box up with them. Is your name Tyler? So I'll call it box T for Tyler. And I'm going to take the values and I'm going to repeat them for counts number of times. Okay, so let's just take a look at that box. We have 9 zeros and 1 10,000. So I can sample from that box. How big do you think I need to sample? A million before you get to the normal? You're a pessimist. What values have we seen so far? What have our draws been so far? A few more than 10. What numbers have we drawn so far? How many times have we drawn? We did 10, we did 100, and we did 250. Well, I'll start with 100. And replace equals true. Thank you. I'm looking at that going, why are there 4s? Okay, thank you. It's box T. And there we go. There are lots of zeros and a few thousands. Okay, so if I then say sum of this guy, then I'll get numbers like, okay, that was 80,000. Am I always getting this? Oh, there we go. 110,000, 80,000, 70,000. Okay, so, there's a big one. Okay, so now what I want to do is I want to look at the sums, and I will replicate this. I'm going to replicate it 100,000 times of the sum of the sample, all of this stuff. So you see what I'm doing here is I'm drawing from the box 100 times and then adding it up. And I'm going to do that same thing over and over 10,000 or 100,000 times and then say, well, that's roughly like, that will be close to my empirical distribution. So now I'm going to say plot of density of sums. What do you think? Oh, what do you think?
I think that your kernel is weird.
You think my kernel's weird? Why does it look like that? Yeah?
I think it was picked out because you can either get a 0 or you can get
Or 1,000 or 10,000? I can't remember. What did we put in there? Was it 1,000 or 10,000? 10,000? Right.
So, like, you're not getting numbers in between.
Right, and that's exactly, but it still kind of looks normal, doesn't it? So what do we expect from the box? Well, we can expect whatever is the mean of box T is, it's 1,000, okay? And what's the standard error? Well, we could take the square root of 100 times the box. Here, let's do it times the box SD, which is the square root of of the box minus 1,000. So it's a 10,000 in there, so the average is 10,000. Does that make sense? Squared divided by 10? Oh, yeah. No, it's the average. I'm subtracting the box average. There is a 10,000 in there, but I've got one 10,000 and 9 zeros. So the average is 1,000. Yes, it should be. Did I not write it? Yes, thank you. It should be box T. Oops. Oh, how about summing it up? That would be a good thing, huh? There. So that's 30,000, right? Okay, so essentially, now if I add on top a normal curve, which has a center of 1,000 and a spread of 30,000, oops. Okay, now what I do wrong? That doesn't look good, does it? Let me go back and plot my, let me plot my sums again. So have I I didn't multiply it by, my expected sum is 100 times 1,000. So my curve should be 100 times this. So I add 2 more zeros. That should work. Oops, I forgot to say add equals true. Okay. And let's make it red just so we can, just because we can. There. What do you think? So do you think if I took the area of those guys, the area, and compared the areas, that I'd be close? Maybe. It's looking pretty, it's actually not looking so bad. We could compare the quantiles, or I could go back here and say, well, what if I drew not 100 times, but what if I drew 400 times from this box? Do you think that would improve things a little bit? So now I've got to plot the density of my sums again. Ooh. And add the curve on top, and that should now have a 4 in front of it, and that should be a 6. If I look at that. Not bad, huh? So that works. And that's sort of what we saw with the box of zeros and ones with 9 ones and 1 0. Now what about the box that I had? That was a, let's see, we had that we'll call box D is rep of, what was it, a 0? I don't remember. 1, 5, 25? So why do you think I've done this? Why have I made this box? And I have 5 ones, 5 zeros, 3 ones, 1 5, and 1 25. Why do you think I made this box? What do you think?
You're trying to make it so that there's an average around a low number with a long tail.
Yes, I'm trying to make it such that it's a very skewed box with a very long tail. That's right. And so I can then come back and just repeat my, so let's find out first what the average is of the box. 3.3, not a very nice number. And then we can figure out the SD of the box. And if I draw 100 times, well, let's just figure out the SD of the box. What do you think the SD of the box is? Can you guess? What's a good guess? See what the box is, 5 zeros, 3 ones, a 5, and a 25? Okay, so will the SD be 10? Higher or lower? Lower. Good. Okay. 7.37. All right. So now we can, so let's now plot what we got from our, did we replicate it yet? No. So we can now, did we do this? No. So let's have sums D. So now we're replicating 100,000 times and with 400 draws. And then we can plot it. Oops. Shoot. Look at that. So I don't even have to put it on top, do I? So it looks pretty normal. So as one of you was asking, well, what does the central limit theorem say? It says that if I have a large number of draws from the box, no matter what the box looks like, the sum of the draws, the probability distribution for the sum of the draws is approximately normal, regardless of the distribution. The center will be at n times the box average, and the spread will be the square root of n times the box SD. Likewise, if you could do the same thing for the average of the draws. So the probability distribution for the average of the draws will also be approximately normal. Now the center is going to be the box average, because we're dividing everything by n. And the spread will be the box SD divided by the square root of n. So the spreads, as we know, get smaller. But both cases give us a normal distribution. So you might ask me, how large is large? How many draws do you need to take for this to happen? And you can now, from what we've seen in class so far, sort of say, well, you know that if you have something really symmetric, it doesn't take very many draws. N doesn't have to be very large at all. But we saw when you have something really skewed that you had to take quite a few draws. But in all the cases that we were looking at, by the time we got to 250 or 400, things were looking really normal, even though we had a very skewed box. In one case, we had all of one number and one really large number far away. In another case, we tried to create something that had a very long right tail. So that's the central limit theorem. And you know what? Rather than go on, I've got one more lecture on wrapping up hypothesis testing. But why don't we just end class early today, and I'll see you all on Wednesday.